everyone. So I'm Rudolf, and I would like to present you the results of my investigation from a capstone project I've done for the machine learning nanodegree of Udacity last year. And so I have only 40 minutes, so there is a lot of technical stuff behind reinforcement learning and deep learning, so I'm going to go fast, just to update you on the most important topics. But I have a GitHub repo where you can find the report of this project, and then there are all the details. There are many pages explaining also the techniques behind that. Okay. So what was my motivation for this project is, I mean, in '97 I was a long time ago. I was studying engineering, and we had some courses and also some projects. It was not possible to implement anything, so there was no real application of that. It was more kind of linear algebra and not more. I was also fascinated by playing Doom in multiplayer mode. So I don't know if you know Doom as a video game. It's I mean, if I say Fortnite, you know it. So it's the version of '97 of Fortnite. And multiplayer mode, it's quite interesting because at this time we had to connect PC with a cable, with this RJ45 cables at this time. So yes, it was a lot of crafting exercise, big crafting exercises. And 20 years later, so I was curious about what are self-learning systems, and I remember some good courses about neural networks, and I said, okay, now I need to apply that. And I said, okay, let's start with the machine learning nanodegree at Udacity to, refresh my knowledge first, and then go for a capstone project on this one. So what I wanted to do is to combine deep learning and reinforcement learning together, and I mean, in a funny context with a Doom, with a video game environment. This is what I wanted to do, and this is what I've done. So from what is reinforcement learning? I know you know that. Just a quick refresher. It's an agent that evolves in an environment, and that takes actions, and that observes the rewards it gets from this. So this is kind of trial and error learning, or is it reward learning, what I say, with reward being positive or negative. The biggest advantage of reinforcement learning is that you don't need any data set, which is great, but you need an environment. So this means that you need an API to have an agent really interacting in his environment. And I think the API for Fortnite is not available so far. So. From a mathematical perspective or modeling perspective, what we use is MDP, so Markov decision processes. So this is the situation where you move from one state to another. You take the decision to move, for example, from S0 to S2, and then you get 0.25 reward, whatever it means, whatever the reward means. But this is, in fact, a mathematical framework to modelize transitions, in fact, in a given environment. And here, for a video game, a state of a game is the image, in fact, the agent or the player has. So the image of where you are currently, whether you have a monster in front of you or not, or an open door, or then this is the stage at time t. Okay? So after that, when you are in this situation, then you decide to take an action, and then you collect the reward of this, and then you move on to state. The NDP is in fact the list of all these transitions with the state, the action, and the reward at the time t, and the next state. And one game or one episode is in fact the finite sequence of transition. A finite sequence of transition is very important for this MDP concept. And what's also very important is the probability of the stage, of being in the state +1 is in fact a function of t and at. So let me move on. So what we use based on this MDP framework is we use a Q-learning algorithm, which is in fact approximated by the Bellman equation. So it's a model-free learning. I'm just repeating that. So the agent learns the policy through training. So this means I'm not telling this agent or this player what a monster looks like, where there will be then most likely negative rewards. I'm not telling him what is the goal. I'm not telling him it's completely blank. So this means that the agent needs to learn by trial, you know, what it is that he needs to do to get to positive rewards. Okay, and we use this Q-learning algorithm to get to the policy, because in fact, after this trial and error phase, then we get to a situation where the agent has learned this policy P from S, which is the maximum of the Q values for a given state and a given action. So you have here the formula for this Q algorithm, where you see that there is a discount factor gamma, which is in fact, I mean, typically between 0.1 and 0.99. It is in fact the way you discount rewards in the future. So in fact, this is this Q learning function optimizes and maximizes the current rewards on the future rewards you will get. Okay, and on this function, then we do then the stochastic gradient descent on this, and we do the backpropagation of the reward through the state space, and we average over many trials and many epochs. So this is again the next best action, or from an intuitive perspective, the Q function is a lookup table where you have rows, a lot of rows with, you know, which are the states, and be careful because these states are already very big because these are already pictures. So you have rows with states, and then you have columns which are the, and for a given state, for a given row, then in front of each action, then you have a Q value, which is, I don't know, maybe 20, 40, and the algorithm, you know, decides on what is the biggest value to take the next action. So it's a lookup table if you want. I mean, this is intuitively like that it works. So this is the pseudocode, and you can see how the Q values are evaluated, and also alpha is a learning net rate. So this is a very important parameter you can use also when fine-tuning this exercise, this model. So I've taken the smallest possible pictures from the VizDoom environment. I'm going in a few minutes to explain you what is this VizDoom environment. So if you have a state of it's a picture of 30 by 45 with 256 gray levels and 3 possible actions. So for example, going to the right, going to the left, or fire. So you have already a state space of 1 million dimension. So you can see that it's already a lot of calculation ahead to explore this state space and to understand, you know, where are the positive rewards, where are the negative rewards, to train the network. I mean the CNN we are going to use, and in order to have a model that takes the right decisions, the right actions when performing a new game, right? So CNNs are perfect candidates for these Q functions because of a local connectivity. Improbable pixel combinations are, you know, taken out. I mean, from this 1 million dimension, in fact, there are many cases which are not going to happen. So there is nothing to learn out of them, so they are not relevant. And CNNs are good at finding features from structured data like images. And specifically for the implementation, so sure, we use fully connected layers at the end for the decision on the different actions on the Q values, but we don't use any pooling layers. I'm sure you have already played with CNNs and trying to discover, for example, or recognize objects in pictures and so on, and you use pooling layers because you don't care about the position of these objects and so on. You just want to categorize this. The problem here is we want to know where the monster is, for example, you know, to have a set of actions to go there and fire at him. Okay. So from this stochastic gradient descent, we use this loss function at the bottom. Again, it's explained in my report how we get to this, and the idea is to train this CNN as quickly as possible, because the challenge is the agent starting the game, which is starting the game, doesn't know what are the goals, doesn't know where are the traps, doesn't know where it gets positive or negative rewards. And the CNN that you use for the Q value has also randomly initiated parameters, so the weights and the biases of the neural networks. So we are completely blank. So this means that there will be a lot of exploration at the beginning to understand where are the positive rewards. And before the CNN gets valuable data to train itself. At the beginning, it will train with bullshit data. That's really the name. So this is the architecture that I've used. You see the convolution layer here. You can have 3 of them if you want. I mean, it's just a simplified version. For one of the scenarios I was going to show, it's enough. Only one is enough to get the features out of the pictures of the states, and then a fully connected layer of 128, and then the Q values at the end, these 3 on the right. So this is for the first scenario where you can only take 3 actions, going to the right, going to the left, and fire. But there are some other games where you can take 10 different actions, like for example, going forward, going backwards, or jumping, or actioning a door. So here, this is an example with 3 actions. You might have more than that. And it's most likely that you will need maybe another fully connected layer in between because of the number of actions. So we use also a replay memory because now, I mean, we got it. The agent needs to explore the state space. The issue is we need also to train the network in between. And this is how it works, this replay memory. So we initialize the replay memory, we observe the initial state, we take an action, and then we observe the reward, the new state, and we store the experience in this replay memory with the state, the action, the reward, and the new state, okay? And then we take a sample of this, and in my report here, I'm taking batches of 64 or 128 randomly chosen transitions, or I mean experiences from this table to train the network. So you see the calculation of the target at the bottom and the loss function on the right. There are some better techniques to do that. I will come back to this later also. So exploration, exploitation. So this is what I said at the beginning. I mean, you take random actions because you need to explore the state space. So you don't know where are the rewards, so you really need to discover them. So this is why, I mean, this is just one little piece of code for this. You see that you can craft an exploration rate, EPS, that decreases over the epochs in order that you go down with exploration with time and that you do more exploitation later on. Where instead of doing a random action, you get the recommendation or the next best action from the neural network. Okay? So this is the VizDoom environment, and it's a great one because I mean this is a research platform for reinforcement learning from raw visual information. Okay, we got it. It's developed and maintained by Michal Kemka and team from the Poznan University of Technology in Poland. And there are many tutorials. The repo is great. Their homepage is also great. They have developed the API. They give a lot of examples. So I mean, within 2 or 3 hours, I mean, first you need to install the VizDoom environment, but this is done in maybe half an hour. In 2 or 3 hours, you get already, you know, the first results without fine-tuning anything. You get something which is already very, very interesting, specifically for the easy scenarios. So this is the API. So for the first thing, you know, this is something that we know, you know, just to start a game. The most important one are the one at the bottom with the get state screen buffer, which is, in fact, you know, at each time you advance by a tick in the game, then you get a state, which is the frame. So this is the function to do that. After you decide on an action, and then you use this make action to do the action, and then you get the total reward at the end. So to calculate that and to understand, you know, I mean, was it a positive reward, a negative reward? So what was in fact the results of my action, and is it something I need to? I mean, is it something which is very important for training the network or not? So I've done my experimentations on a CPU. So this is why at the beginning I started with small size pictures and small resolution. A 3 gigahertz AMD, Ubuntu 16.04 on that, the VizDoom 114, Python and TensorFlow for the CNN. So you see, you can do reinforcement learning. I mean, deep reinforcement learning today on a CPU, which was something just unimaginable in '97. Even doing, even neural networks with only 1 or 2 layers was already not possible. But what's for sure is for Christmas I have already ordered a GPU because sometimes I had my PC calculating the whole night on some of these exercises. So these are the 3 different scenarios that I have investigated. So I'm going to show you, these are the random walks, so there is nothing interesting in that, just that you understand what a scenario is about. So the first one is a scenario basic. So you have a monster. Oops, it's not showing. So you have a monster at the wall on the right, and you are the player here, and the only 3 actions is fire or go to the right or go to the left. Okay, it's just random actions, nothing very interesting. The next scenario is about health gathering. So this means that the player is on a lava floor and is losing health with time. So he needs to collect this medkits. To navigate and collect these guys in order to not to die. Okay? And the last one is the deadly corridor. So it's difficult to see that there is a. I'm going to reply to put it again. So at the back there is a green jacket. This is the objective we need to do. But on the way there are some people in this corridor shooting at him. So he needs to understand, he needs to do combine actions with, targeting at someone, firing, and also navigating towards this thing. So nothing very interesting. Now, I have implemented that with a standard DQN. So for the basic one, I'm going to show you that in a moment. So we are in fact in a fully observable area. So this means that every information that is needed for the different transitions and different states is available here, which is not the case for the other scenarios, which are in fact more challenging for DQN. So with one convolutional layer and 40 epochs, you get an excellent results, and I'm going to show that in a second. For health gathering, one convolutional layer and 40 epochs, navigation is okay, but it's more or less okay, I would say. And for the deadly corridor, targeting is more or less okay, but navigation is a bit difficult. So let me go to the videos now. So I'm playing 10 times this game. So each time this guy is successful, you see that you are changing to the next game. So you see that it's pretty impressive, in fact. So I've not told him that this is a monster, so he recognizes it. He goes to there. He takes the actions to go there and fire. Just playing it again. So he has learned the policy. I mean, this is the conclusion of this. I mean, visually, he has learned the policy. Okay, stopping this. Now going to the health gathering with standard DQN. So here he needs to pick the medikit. So the navigation looks good. If you are attentive, there are also some blue bottles. So these are poison bottles. So he should not pick them up. So this is negative rewards for them. But he picks them up. So the navigation is great, but he has not learned really to make the difference between, what is, this white cross on a green background and what is blue and so on. So it's playing 10 times this episode, as illustration. So this is also impressive. I mean, the navigation works quite well. I mean, even if you have the impression that sometimes he's kind of, taking some, overshooting on the actions he's taking, sometimes too much right, too much left, and so on. So I'm stopping this. I'm going to the last scenario, VDQN. And you will see that, let me start at the beginning because I think the first one though is the best one of all. So it was quite close to the green jacket. So this means that he has learned, maybe by chance, from the training perspective, that the green jacket has the maximum reward. So he has learned that. What he has not learned is, to go right, fire, go left, fire, advance, and then go right and go left, and so on. So he's just, he just gets killed on the way to the green jacket. I think this is a very challenging one, even if navigation is straightforward because he needs to go, straight to the green jacket. So these are the results for this one, for the standard DQN. I mean, it's quite interesting to see that. I'm not going to detail everything, but you see, these are, again, the three scenarios. And you see for the basic one that the testing and training are going well. So on the left, on this axis, these are the points from the rewards is accumulating. So it's going slowly to the maximum. And here, this is the loss function, which converges to 0 quite, not quickly, but after 40 epochs. So 40 epochs is 40 times 6 minutes roughly on the CPU. For health gathering, you see that it's a bit a nightmare. Training, testing, sometimes you think he has learned a bit. So I don't know, maybe the solution would be maybe to stop at epoch 23 or 24, and let's say, and stop there and test it. It's very noisy on the loss function, which is also not converging to 0. After 40 epochs, you are still at 200. It's very much. And for the deadly corridor, a kind of asymptote, it kind of is limited in what he's learning or what he can learn. I don't know. There is, and the loss function is kind of oscillating. So it's really difficult. So, and these are the challenges, in fact, in reinforcement learning generally. The temporal correlation. For example, in the first scenario, when the agent needs to go, let's say, 10 times to the right and then fire, the problem is he gets the reward when he fires the monster. At this time, he gets the reward. So he might think, okay, firing is the action that brings me the reward. So I have learned that firing is what I need to do. As I was tweaking my program at the beginning, and I had only 3 epochs, just to get it run, and understood that he's doing the right thing. And after the 3 epochs, the only thing he had learned was firing. So when I played with this model, then it was just firing, not moving, no navigation, nothing, was only firing. What I would like to say is, at the time he gets the the reward, then he thinks that this is the right action. But in fact, it's not this that made him successful. What made him successful, it was the 10 steps to the right and then firing. So it was a kind of combination of actions before he could get the reward. So this is this temporal correlation, which is very difficult to get out. So the replay memory is already helping because, as I explained before, to train the network, the CNN, you take randomly chosen batches of 64 transitions or 128 transitions. So you kind of get rid of some of the temporal correlations, but it's not completely out of this. The fully and partially observable environment, so the Q-learning models makes a strong assumption that the agent has the full knowledge of the current state of the environment, which is possibly the case in the basic scenario, but not in the others. Specifically for health gathering, where the maze is generated every time. Every time a new maze on this lava floor. Okay. Overestimating action value. So this is a more difficult topic here, and we have only 40 minutes of surgery. So I think I'm not going to deepen this one. It's in fact the approximation of the maximum expected action and maximum action value. This is something we need to, in fact, to separate. The evaluation and the selection of the action needs to be separated. And as explained, spares and delayed rewards. You know that at the time you get the reward, it's because maybe you have done good actions, maybe 20 ticks before in the game. It was not the last action. So I have implemented a double DQN, which is something that has been proposed by Van Hasselt in 2015. And the issue with standard DQN, as I already said, is the operator uses the same values to both select and evaluate the action, leading to an overestimation. And here we can, in fact, decouple this the selection and the evaluation in order not to have this overestimate. It looks complicated, but it's not. If you have already a simple standard DQN implemented, it's not so difficult to implement a double DQN. It's just that you need to have two sets of weights and biases for VCNN, what we call the target network and then an online networks, and they are used separately to select or evaluate the action or the Q value. And there is the target network is a periodic copy of the online network. So it sounds very complex. The only thing that needs to understand is how to transfer biases and weights in TensorFlow from one network to the others. I mean, if you got this, then it's doable. Dueling architecture is a second improvement that I've implemented. So you can see on this picture. So the first picture is the standard DQN. At the bottom is this dueling architecture where you separate a value function VS from the action or advantage function A as a function of the state and the action. So this is here, where in fact you just copy the output of the vision network and recombine them at the end. The recombination is a bit tricky, but the calculation, you see the formula is quite easy to implement. I mean, it's very easy. So, and then I'm showing new videos for that. So just, you will see for the simple scenario that 80 epochs and one convolutional layer is enough, so it works well. For health gathering, it just doesn't work. For the deadly corridor, targeting is okay, but what's not convincing is a navigation. So let me show you that. So dueling double DQN for the simple scenario. So, I mean, an improvement with dueling double DQN was not necessary, in fact, because it worked already with a standard one. Just wanted to see that we're not destroying the model with these new things. For the health gathering, so it just doesn't work. Doesn't work at all. So there is some navigation, but I mean it's really erratic. Okay. So I think he has only learned to scrub the wall, except this. It's not really convincing. I'm stopping this. What's more interesting is on the deadly corridor, because this time he has learned, for example, you know, to target the guys on his way to the goal. I mean, it's still not convincing, but it's a bit better than the standard DQN. So, for example, in that case, he has targeted the two guys very quickly, and it was very good. But the navigation just doesn't work. Okay, so I'm stopping this also. Coming back to this. Okay, and now these are some other techniques that I have investigated but not implemented. So, for example, the prioritized experience replay from Charlotte et al. So, it's when you build up your replay memory, you add another. You not only store, you know, the states, the action, the reward, and next state. You also store the temporal difference, and the temporal difference is in fact the highest of the difference between the initial Q value and the Q value which has been effectively measured or calculated. So. Here, in fact, it shows the importance of this transition. And the trick here is, in fact, when you select your batch of transition to train the network, you take the one with this kind of importance in them, with this temporal difference as a high number, instead of taking random batches of transition. You just, you know, focus on the one giving information, whether it's negative or positive rewards. These are the transition which contain some information that needs to be trained and put through the neural network. A3C, or Async Advantage Actor-Critic, it's a bit it's a difficult one. I mean, to explain that in a metaphor, it's a bit, you know, you have children on a playground playing, and you are the adults, you know, taking care of them, and they are the actors, and you are the critic, and you say, you know, don't do that, or yeah, you can do that. This, no, okay. But if you have 10 children doing that, or 10 entities, 10 software entities playing the game, what you can do is you can learn from all the experiences these guys have done, and all the experiences with good or bad rewards and so on, and have a kind of consolidated model around that. So this is quite powerful. Direct future prediction, or DFP, is one that's been shown last year from the guys from Intel. Tuzovitsky is based in Munich, and what did you, maybe I'll show you the architecture. It's, I mean, even a level further from an architecture perspective. So you still recognize the image that gets put in, you know, the state in the blue box. But what you have, we also put, you know, the goals and the measurement. And the measurement, as for example in health gathering, it's, you know, because you are on the lava floor, then you get, you know, at every tick, you know, a decrease in your health. So this is the kind of measurement that can be in there. So instead of waiting for the end of the game to have the total reward, you get a kind of constant measurement on what's taking place here. And then you separate in expectation and action, as we said before, which is very important features to get rid of some of the drawbacks from reinforcement learning. And then you recombine them at the end with the prediction and a target, which is, in fact, it's a bit more of supervised learning, in fact, because there's a prediction, than really a reinforcement learning. But this is interesting because you have this separation between expectation and action. And I'm showing you this video here. This is a video that has been done by these guys from Intel, and it shows you the different scenarios and the different, the performance of different algorithm on the different scenarios. So here it's DQN, so you recognize this basic. So there is no maze in between here. It's just pick up the medkits in order not to die. So now it's A3C. So you see that there is a smoother navigation, and this is their approach, this DFP. So here again, you see that there is a smoother navigation. So here you recognize again the health gathering scenario with the maze in between, and with the poison bottles in blue, which shouldn't be picked, but they are picked by the DQN, they are picked by the A3C, and you will see with this DFP that they are not getting picked, which is quite amazing. So this is the DFP approach from Intel, and you see the navigation is perfect. The targeting of the medkits is very good, and they don't take the blue bottles. They don't pick up the blue bottles. So what's quite interesting here is, just begin break, is in fact together with the VizDoom environment, which is provided by these guys in Poznan, there is also a tool to create new levels and modules. So if you are interested, in creating your own levels and so on, I mean, it's possible to do that. So I've not done that, but I mean, it's quite crazy, in fact, to reinvent Doom. So this is one of the stages they have created, and this is the DQN. So you see, it's just completely overwhelmed by what is taking place here. So F3C is a bit better. You see that he has learned a bit more than the standard DQN. But it's still, not very smooth from a navigation perspective. And this is the DFP from there, which is, I would say, more, the way a human being would play, I would say. So there is a maze, there are monsters shooting at you. So the complexity increases. And there is a second battle scenario we have developed for this. So DQN is again scrapping the walls. A3C tries to target some of the monsters. And DFP is a bit, is more active. You can see that. I mean, he gets shot also sometimes, from the monsters. So he hasn't learned everything, right? But I mean, it's already a good improvement. So I'm almost finished. So there are also further techniques. So for example, imitation learning, which is in fact you have a human being playing the game, and as he plays the game, you just fill up, this memory replay. Replay memory. So this means that before you start with your agent trying to learn, you have already a memory full of good transitions. I mean, you don't need to play the game very good, but I mean, if you see a door on the right, you go to the right and you go through the door. So these are the kind of transitions that are already helping for it's imitation learning. It's a kind of also transfer learning, from a human being to a machine. So there are some others. I'm not going to detail here. It's instead of leverage CNN, we leverage recurrent neural networks. Here the idea is to keep some information over a long time period. So thanks to the recurrent neural network. So the DRQN, DARQN. This works on some Atari games I've seen in the publication from Hausknecht et al. I think on this kind of complexity for Doom and for video games with partially observable MDPs and environments, I think it doesn't work. And hierarchical DQN are also very interesting. Not implemented. That the idea is, top level actions and lower level actions, so a hierarchy of actions. I think it could be helpful. I mean, conceptually, it would be helpful for the daily corridor where you need to go. I mean, your ultimate goal is to go to the green jacket at the end of the corridor. So this is the top level action. But in between, you need to do a lot of things. Turn right by, I don't know, 45 degrees, shoot, and then go turn left by 90 degrees, shoot, advance by 3 meters, and so on. So a lot of lower level actions behind that. Because I mean, we have seen that also with my video. In my videos, sometimes it's difficult to learn at the same time, different actions. So the navigations and the targeting of monsters. It's very challenging to learn all these things at the same time. Transfer learning, we know that right from, for example, the projects where you want to categorize and detect objects in pictures. What you can do is take or leverage existing models from ResNet 50 or whatever. Just cut the last layer of the network. You extract the bottleneck features, and then you just add 3 layers, and you train the model further on your particular application, So the question is, how would this work with reinforcement learning? It's not so clear. I mean, what's currently being done for autonomous driving is we have autonomous cars or self-driving cars learning in an environment which is simulated. And then the question is, I mean, from this model which has been built from the simulated environment, how we can further train it in a real world. So I think it's still a research topic, right? I mean, we are not going to say it to a car, okay, now you are in Nymphenburger Straße 86, and now you need to go to Berlin and learn, explore and do random actions. Yeah, it's going to be very expensive. So this is my last slide. So my conclusion is, I mean, reinforcement learning, whether it's deep or not, it's still a challenge. I think even with pseudo 3D environments or simulated environments, I think it's still not completely solved. Self-driving cars, for sure. Where it's interesting is for next best action in customer service and one-to-one marketing. That use combination of predictive analytics, predictive models, and adaptive modelings. I mean, this is for example, when you send, for example, an email to one of your customer, whether he opens it and hover over, for example, an action button or not. This might be considered as, for your model, as a reward, a positive reward, and if this customer just delete it, then this is a negative reward. So based on this feedback and signal from what is the resonance of your email, you might then adapt your email campaign. I mean, up to a point where you are targeting people one by one. This is what I call one-to-one marketing. So you don't need to segment your customers in whatever demographics and so on. You have the technology to really address each and every customer as a single person. Yeah. This is what my company Pega is doing. See, if you don't know Pega, then have a look. So the references are here. The resources are also on GitHub. I will provide also the presentation to Sergi. And so thank you everyone for, and if you have any question, then go ahead. Okay.
So are there any questions? Not a single one. Oh, well, we can do better than that. Doesn't play
Doom 2 or Fortnite. Would be great to do that with Fortnite in multiplayer mode. Yes, you're right. Yeah. But there is a World Cup every summer organized by these guys from Poznan, where I mean, you have time to train your agent in a multiplayer environment, and then you submit your player, and then all the players play against each other and so on. And there is kind of World Cup for Doom. Yeah, exactly. That's great.
Any other questions?
No? Okay, you can ask, yes. The shy people, now we're coming back.
Thank you. Yeah, maybe during the implementation, obviously you didn't get the best results directly from scratch. So the question is, what are the good tools to monitor? You mentioned you can have a look at the cost function, checking if it goes down, but what are the other techniques you checked during your implementation to make sure to understand what's going on?
Mm-hmm. So for the standard DQN, I've used the loss functions, as you said, and I've used matplotlib to show it. In the second part with the double DQN and so on, I've used TensorBoard from Tensor to have a look at the loss function. But I mean that's a very good question. I mean, in some of the cases, you see that the loss function is not really helpful to really, give you information about, what do you need to improve in your concept or in your model to improve and so on. And I mean, it was a 8-week project in my free time, and I mean, this is certainly a very interesting next step for this project 2.0.
How much compute time did you have?
I mean, if you have good ideas for me, that would be great. Sorry?
How much compute time did you have in those 8 weeks?
How much what? Sorry?
Compute time, actually, when I was training, basically.
I mean, it was more or less for the more complicated model 6 minutes per epoch. So 120 epochs, and it's 12 hours. So it was the longest computing time on a CPU. So I mean, you can imagine. I mean, I had to start it, before going to bed in the morning and look into the results. But I mean, with GPU, it would be even, shorter by a significant factor. Well, I was thinking of putting all of these models also on the GPU infrastructure from AWS in Dublin, for example. Just say, okay, that's fine.
So last possibility to ask the question? No. Okay, perfect. Thank you very much for the nice talk.
Okay, thank you.